Its effectiveness can be good, but there is the risk of reintroducing contamination. Therefore, means of being able to recover all contamination and debris is essential. Safety is a major consideration. It involves confined space vessel entry, therefore breathing apparatus will be required. For operational reasons, to avoid contamination, slugging and corrosion, most commissioned pipeline systems are required to be clean and dry. Dryness required for a particular system is achieved by degree. Nitrogen, suitable for initial drying, may leave piping damp internally. Vacuum drying, suitable for pipelines, is used to remove all moisture. The photo in the upper right shows vacuum drying with the gauge reading 99 kilopascals, an almost complete vacuum. Refer to the upper embedded file for details of pigging and vacuum drying of gas pipelines. Notice on page 7, figure 4, the duration needed to achieve the required degree of dryness. Vacuum drying is very slow and consequently expensive, but can achieve absolute dryness if this is a contractual requirement or safety consideration. In the lower embedded file, see how this company commissioned and started up one of its pipelines. Notice the techniques deployed and the use of processed liquids. Note also on slides 23 to 26 that having dewatered and vacuum dried the pipeline, it was left inert with a nitrogen blanket until ready to go into service and receive gas. Nitrogen has a low dew point and is therefore suitable as the drying medium of choice in colder climates and subsea pipelines. The gas is introduced from a high energy source to remove water slugging and debris in piping and pipeline systems. Disconnect pipework from all vessels, remove all internals that could cause blockage or obstruction. Place a temporary isolation valve at the exhaust, build the internal pressure and release, removing all debris. It is not to be used for cleaning vessels or tube heat exchangers. Important considerations are to ensure there is an adequate nitrogen velocity with a minimum of 200 feet per second, approximately 65 meters per second. Allow an adequate purge duration of say 12 hours and sample test for dew point temperature, DPT, at system low points. As a guide, continue the purge if the DPT is higher than -30 degrees Celsius. Stop the purge and reinstate when the dew point temperature, DPT, is lower than -30 degrees Celsius. Advantages. The major advantage is its effectiveness for removal of water debris and with measurable results. The disadvantages, and the major disadvantage, is the cost, and particularly in offshore or remote locations where shipment and storage of nitrogen can be very expensive. A specialist contractor will be required with operation by trained users. Further considerations are safety. Restrict access and place barriers around the system or, as a minimum, for a pipeline at the launch and reception ends. Provide adequate containment at the exhaust. Vacuum drying is particularly effective for piping systems and subsea gas pipelines that have previously been flushed to remove all loose debris, but where no moisture can be tolerated. After flushing, specifically sized vacuum pumps are introduced by a specialist contractor to remove any remaining water from piping and pipeline systems. All sensitive instrumentation must be removed first. Vacuum drying is based on the theory of combined gas law from Avogadro, Gay-Lussac, Charles, Boyle and Marriott's law. As the volume of air is reduced, the pressure drops. Also, the boiling point of any liquid present in the system also drops. At an absolute pressure of about 2 kilopascals, water boils at the ambient external temperature of the pipe. The vacuum drying process must be followed very carefully. Vacuum pump speed must be maintained to prevent air being evacuated too quickly, in which case any free water or moisture present will not evaporate as intended but cool and freeze. The pipeline appears to be dry, but after putting it into operation, ice gradually melts and problems with water appear again. Therefore, it is necessary to carefully follow the drying process, including controlled dwell time, when vacuum pumping stops, allowing free water to vaporize into the pipe. Dwell or rest periods are calculated, determined by the internal volume of the pipeline and ambient temperature. Dwell times are designed to prevent the residual free water from freezing. Dwell times significantly prolong the overall drying time. Refer to the graph on slide 216 of a typical vacuum drying operation. Vacuum drying makes the first gas admittance into the pipe much easier. Gas is flowing into a vacuum, the pipe is deaerated and there is no risk of forming an explosive mixture. Slide 216, graph of a typical vacuum drying operation. After depressurizing, any pressure increase will indicate a leak. Find and seal any leaks before continuing the vacuum test. Monitor the vacuum pump exhaust and oil filter for any emulsion, which would indicate the presence of moisture. When a vacuum has been pulled, the pump is disconnected and the pressure reading is stable for the duration specified in the test procedure. Release to atmospheric pressure and fill the system with a blanket of nitrogen. Reinstate and proceed with commissioning. The major advantage of vacuum drying is its effectiveness for the absolute removal of water with measurable results, as compared with nitrogen purging, which will obtain a relative degree of dryness. The disadvantages are principally its cost. It is extremely slow, with durations usually measured in weeks. A specialist contractor and equipment will be required, with operation by trained users. The safety considerations are to restrict access with barriers required. Install containment at the exhaust. Use or modify the A and B check sheets supplied with Zenator to record, track and report progress in the sequence of activities to achieve the internal cleanliness and dryness of tubing, piping and vessels. New check sheets or commissioning procedures should be rendered compatible with Zenator. Referencing the project's new check sheets or commissioning procedures within Zenator will enable the tracking, controlling and reporting of progress, all immediate and impacting activities such as punch listing and management of change. For a reliable audit trail, use or modify the isolations with isolations removed feature in Zenator to record, track and report the removal of internals or installation of spools for temporary purposes. Make sure you attach scanned copies of the marked up piping isometrics and P&IDs in Zenator.
The scrubber at the Dry Fork station is unique.
It's the largest reflex circulating fluid bed scrubber in America, volume-wise.
There are smaller power plants that use a similar scrubber, but the one at Dry Fork station is much bigger. It's a design by Graf Wolf, a company based in Germany.
Our permits for this project are pretty stringent, and they were able to prove when we were negotiating with them or during the design phase that they can meet our permit levels.
Not only has the scrubber been proven to meet very strict air permits, it does it with less water than the scrubbers at most power plants.
You look around Gillette, you notice we're not a water-rich area. And so any time that we can reduce that water use is a huge plus for us. The same reason we use an air-cooled condenser instead of a conventional condenser.
Nolan Bray and Jim Lund are Basin Electric engineers in charge of getting the scrubber up and running.
Graf Wolf has been here the whole time to walk us through this process, and I feel very confident this scrubber will perform just like they said it's going to perform.
This is how the scrubber works.
We take the flue gas coming from the boiler in 2 streams. It combines into the bottom of the absorber vessel. It goes through 7 Venturi nozzles which straighten out the flow.
After it enters a Venturi, it actually accelerates. And the acceleration is due primarily because we want to establish the circulating fluidized bed of lime and ash.
The bed of lime and ash isn't a solid mass at the bottom of the scrubber. It's a floating mass of lime and ash, and it works sort of like a filter.
We accelerate that flue gas so that it has enough oomph to keep this bed floating.
The scrubber is 200 feet tall. The bed is between 50 to 70 feet tall.
The whole idea of the bed is it gives it a place for the reaction to happen.
The bed is where the sulfur dioxide is captured. It's the calcium in the lime that captures the sulfur. More fluidized lime is added when needed.
We add just enough water to increase the surface area of the calcium for improved sulfur capture, but it's still a drier product.
The gas moves from the scrubber to the bag house, where 15,500 bags capture ash, drop it into hoppers, and then route the ash back to the scrubber where it can be used in the bed again. The system must work flawlessly before any coal is burned at Dry Fork Station.
The milestone that we're looking for is to be able to establish a bed, have it operate at that set point, so that we can say, let's introduce coal, let's introduce flue gas, because we know that we can handle that.
At Dry Fork Station with producer Greg Wheeler, I'm Tracy Bettenhausen.